So we've talked about piezoelectrics and how electricity becomes vibration and creates waves. We've also talked about pings and pulses, and we've drawn images like this one. But when we talk about sonar, we usually use the term beam. So what is a sonar beam, and how is it different than these waves we've been drawing? Imagine we have a bomb that we are going to set off underwater with some kind of waterproof fuse or something. That bomb would generate a pressure wave, and if we listened for the return at our ship, we would then have a working sonar system. This is actually a concept that was used in early acoustics research to generate sound underwater relatively easily. One drawback, among many of course, was that the sound was being generated in all directions, when you really only cared about one specific area. You'd waste a whole heck of a lot of energy sending waves back up to the surface for no good reason. If you look at single beam sonar, it handles this problem really well. It manages to focus that energy down to a narrow angle, or beam, that extends towards the sea floor. That angle depends on the frequency and dimensions of the sonar. A high-frequency sonar, or a sonar with a large transducer, is going to generate a narrow cone of energy. The relationship between frequency, the length of the sonar ray, and beam width might be a little difficult to understand at first. Take a look at this visualization showing the relationship between a bat's screech and the beam that it generates. The larger bat has a larger mouth and creates a narrower beam, much like our large sonar arrays. The high frequency or high pitched screeches are also narrower. The most narrow beam is created by the largest bat with the highest frequency screech, just like our large high frequency sonar. But what about multi-beam sonar? I mean, clearly multi-beam has multiple beams, but how are they formed? Well, multi-beam sonars are composed of a transmitter and a receiver. They are generally in a Mills-Cross arrangement, where the transmitter is pointed fore-aft, and the receiver is oriented across track, forming a sort of T or cross. The transmitter is composed of multiple piezoelectric elements, all in a row called an array. It is going to emit a pulse of energy that is narrow in the fore-aft direction, but wide along track. This is possible due to the same principles we talked about earlier, where the frequency of the pulse and the size of the transmitter control the shape of the generated wave. The receiver is a bit more complicated. Just like how the transmitter is aligned to send out a wide pulse in the across-track direction, the receiver is an array of elements aligned to receive a wide pulse in the fore-aft direction. What you find is that the sonar is able to see only the intersection of these two areas. That intersection is basically a beam received at the receiver, pointed straight down, much like single beam sonar. So how is this any better than single beam? Well, multi-beam sonar has some fancy electronics that allow you to adjust where the receiver looks for return from the transmitter. It can move that beam along the transmit pulse just by adding in a time delay to account for the difference in the received wavefront. So that gets you a single steerable beam. But remember, the receiver array is composed of many piezoelectric elements. If we add multiple receiver circuits or channels, we can use different parts of that array and have them all listen at the same time, trying to cover the area of the seafloor insonified by the transmitter. So now we have multiple steerable beams that we can use to form a wide angle of reception, known as the swath or footprint. Let's look at one quick example of a multi-beam sonar. Here we have the Rezon 7125 SV2 specifications sheet. Take note of a few things. The sheet lists both a transmit and a receive beam width. This makes sense because we know now that these are two physically different things with their own orientation. Using the 200 kHz frequency, this system can put out 256 beams, all with a 1 degree by 2 degree beam width. As we expect, the high frequency option allows for a more narrow beam width. Finally, we can talk about angular resolution, or the ability to see targets along the path of your swath. It's basically just related to beam width. If you take a Rezon SV2 400 kHz beam with an across-track beam width of 0.5 degrees and a depth of 30 meters, you'll insonify about 0.26 meters of the sea floor. If you get two small targets that can be covered by your 0.26 meter footprint, you're only going to see the target that provides the strongest return. That's a problem if you're looking for lots of small things, like masts or pilings. It also helps if you have multiple returns to really confirm that you are seeing that target. One dot does not a feature make. Anyway, this video was a little technical, but I hope it cleared some things up for you. Thanks for watching, and good luck out there.